Hello everyone, welcome to the third video lecture on communication networks and transmission lines. In the previous lecture, we have seen some of the characteristic parameters of a symmetrical network, that is characteristic impedance Z0 and propagation constant gamma. Also, we have seen the expression for determining the characteristic impedance and propagation constant for a general network using the short circuit and open circuit impedances ZOC and ZSC. So we'll be continuing that discussion by taking the examples of a general T and a pi network and trying to find out the characteristic impedance for a T and a pi network. Also, we'll find out the propagation constant gamma for a typical general T and pi network. Then we will try to establish a relationship between these. Also, we will take up the example of a lattice network, a general lattice network, and try to find out its characteristic impedance Z0 and gamma for a lattice network. So before we start with this lecture, let's recollect that numerical problem that we have done, in which we took a typical T network in which we had inductors in the series arm and a capacitor in the shunt arm. So these inductance values were given, the capacitance value was also given, and we have found out the propagation constant gamma for this. So our conclusion was that attenuation constant alpha was equal to 0. So the peculiarity of this network is that this network is consisting of only purely reactive elements. There is no resistance coming in this network. So we have found that for such networks, the attenuation constant alpha will be equal to 0. The network will only offer a phase shift. So we have found that only the phase constant or the phase function beta was present in such cases. So what happens in the case of a network which is consisting of only resistances or resistive elements? So we will examine such a network by considering a T network as shown. Let 100 ohm be the series arm impedances. The shunt arm impedance be 400 ohm. And we will try to find out the gamma for this particular network. So we know that tan H gamma is equal to root of ZSC upon ZOC. So what is our short circuit impedance ZSC? We will short this end. So the net impedance will be this series with parallel combination of 400 and 100 ohm. So ZSC is equal to 100 plus 100 parallel 100. So this will evaluate to 80. So the short circuit impedance ZSA will be equal to 180 ohm. What about the open circuit impedance ZOC? So we will open this. So the impedance will be this impedance series with this impedance. So it is 100 plus 400 is equal to 500 ohm. So what will be tan H gamma? Root of 180 divided by 500, which is equal to 0.6. So we see that on the right hand side we are having a real quantity, whereas in this previous example on the right hand side we had a purely imaginary quantity. So that's the difference. So on taking the inverse hyperbolic of this quantity, we will get gamma is equal to 0.6931 angle 0. So we have only attenuation function, and beta is equal to 0 here. So this is our e power alpha. So we have e power alpha is equal to 0.6931 plus alpha is equal to natural logarithm of this minus 0.358. The unit is Nepper. The negative sign shows that the signal is losing its amplitude, or in other words it is the opposite of gain. That is, attenuation is happening when the signal is passing from the input end to the output end. And what about beta? Beta will be equal to 0 degree. So see the difference between these two cases. So when the network is consisting of only resistive element, we get only the attenuation constant and the phase shift will be equal to 0. And when the network is consisting of only purely reactive elements, we will have 0 attenuation, whereas the signal will be phase shifted. Okay. Now we will take a general T network and try to find out an expression for its characteristic impedance. So we'll find out Z0 for a T network. So this is our typical T network. We'll take the series sum impedances such that the total series sum impedance will be equal to Z1. So the impedance of one of the element will be equal to Z1 by 2. So that the total series sum impedance will be equal to Z1 by 2 plus Z1 by 2, which is equal to Z1. Also Also, the total shutdown impedance will be equal to Z2. So since we are having only one shunt element, so this should be equal, the value of this shutdown impedance should be equal to Z2. So this is our general T network. So this is the input port, this is the output port. So we know the general expression for the characteristic impedance, which is equal to the geometric mean of the short circuit and the open circuit impedance. So what is the short circuit impedance ZSC? So it will be this impedance series with parallel combination of these two impedances. So ZSC is equal to Z1 by 2 plus Z2 parallel Z1 by 2. So that will be equal to Z1 by 2 plus Z1 Z2 by 2 by Z1 by 2 Z2. Now we will keep this quantity as the denominator and bring this term to here. So when we multiply these two terms, the numerator will be Z1 square by 4 plus Z1 Z2 by 2 plus this term Z1 Z2 by 2, the whole divided by Z1 by 2 plus Z2. So that will be equal to Z1 square by 4 plus this plus Z1 Z2 by 2 plus Z1 Z2 by 2, that will be equal to Z1 Z2. And the denominator will be keeping as such for the time being. We will evaluate the open circuit impedance ZOC. So that will be the series combination of this impedance plus this impedance. So ZOC is equal to Z1 by 2 plus Z2. So this will be labeling as 1. This will be equation 2. So what is the product of the short circuit and the open circuit impedance? So we will multiply this ZSC with ZOC, this. So when you multiply, this will come in the numerator and it will get cancelled with this denominator. So in effect we will get the numerator, that is Z1 square by 4 plus Z1 Z2. For convenience sake, we will rearrange this term by taking out Z1 Z2 as common. So this is taken out, so here it will be 1, and we take one Z1 out of this, so we have one Z1 here. The denominator we multiply 1 Z2. So what is our characteristic impedance for this T network? So Z0T, because this is the characteristic impedance for a T network. So that is equal to square root of ZSC into ZOC. This is a general expression. So we have, for this particular T network, we have ZSC into ZOC is equal to this quantity. So Z0 T is equal to square root of Z1 Z2 into 1 plus Z1 by 4 Z2. Okay. This is the expression for characteristic impedance for this particular T network. As we will see the case of a typical pi network. a general pi network and try to find out the characteristic impedance for a pi network, that is Z not pi. So characteristic impedance Z not for a pi network. Again we draw the network. Following, keeping these things in mind, the total series sum impedance will be equal to Z1. Since we are having only one impedance, the impedance value of this element should be equal to Z1. And here we are having two shunt arms. So the total shunt arm impedance will be equal to Z2. So what should be the impedances of each of these elements? So each of these should be equal to twice of the Z2. So that the total shunt arm impedance will be equal to 2Z2 parallel to Z2. So that will be equal to Z2. This will be the input port. This will be the output port. Again we use the same formula, that is the characteristic impedance is equal to the product of square root of the square root of the product of short circuit impedance and the open circuit impedance. So what is the short circuit impedance for this particular network? We will short this. So it will be equal to the sum impedance parallel with the sum impedance. So 2Z2 parallel with Z1. So what will be 2Z1 Z2 divided by Z1 plus 2Z2. We'll keep this and then evaluate the open circuit impedance. So we are opening this terminal. So the open circuit impedance will be this impedance parallel with series combination of these two impedances. So we have 2Z2 parallel with Z1 plus 2Z2. So this will evaluate to be 2Z2 into Z1 plus 2Z2, 2Z2 plus Z1 plus 2Z2. So simplifying, you get Z2 Z1 plus 2Z2 by Z1 plus 4Z2. So we will keep it like this, so that from equations 1 and 2, what will be the product of ZSC and ZOC? So this will be multiplied with this quantity. So numerator will be this into this, and this denominator will be cancelling this numerator. So we have 2 into 2 is 4 Z1 Z2 square divided by, this term will be cancelled. So we have Z1 plus 4Z2. Okay, for convenience we will rearrange this term by taking out Okay, we'll bring this 4Z2 to the denominator. So we'll have Z1, Z2, and 4Z2 will get cancelled here, so that it will be equal to 1. This Z1 divided by 4Z2 will be equal to Z1 by 4Z2. So what will be our characteristic impedance? Z0? It will be the square root of ZSC and Z0, ZOC. So we are evaluating the characteristic impedance for this pi network. So we'll write this as Z0 pi, that is equal to square root of Z1 Z2 divided by 1 plus Z1 by 4 Z2. So we got one more expression. And this is our Z0 T. Okay. Now what happens when we multiply these two characteristic impedances? That is for a T network and a pi network. So the product Z0 T into Z0 pi will be equal to, so Z0 T is Z1 Z2 into 1 plus Z1 by 4 Z2 into square root of Z1 Z2 divided by 1 plus Z1 by 4 Z2. So these two quantities will get cancelled. So it will be equal to square root of Z1 Z2 into square root of Z1 Z2. So that will be equal to Z1 Z2. So we get a strange relationship like Z0 T into Z0 pi is equal to Z1 into Z2. So this is for a T network whose total series sum impedance is equal to Z1 and total shunt sum impedance is equal to Z2, and for a pi network having the total series sum impedance is equal to Z1 and total shunt sum impedance is equal to Z2. We can establish a relationship like Z0 T into Z0 pi is equal to Z1 into Z2. That is the product of the total series sum impedance Z1 into the total shunt sum impedance Z2. Now we will take the case of a lattice network and evaluate the characteristic impedance Z0 for a lattice network. So we have seen what is a lattice network. We have discussed its applications also. So we have series sum impedances as well as diagonal impedances. So we will label the series sum impedances as ZA and the diagonal impedance will be ZB. This is our input terminal and this is our output terminal. So in our lecture 1 we have already discussed that we can draw this lattice network in a different form for easy understanding. Okay, we can draw this lattice network like this. Now this will be our input terminal and this will be our output terminal, 2 dash. Now let's try to identify the branch impedances. So from terminal 1 to terminal 2. So while we move from terminal 1 to terminal 2, we come across ZA. So from terminal 1 to terminal 2, we come across ZA. And while moving from terminal 1 to 2 dash, we come across diagonal impedance ZB. So 1 to 2 dash will be ZB. And similarly, we move from 1 dash to 2 dash, we go through ZA. So 1 dash to 2 dash, we come across ZA. And from 1 dash to 2, we come across ZB. 1 dash to 2, so this will be equal to ZB. What is our characteristic impedance? Z0 square root of the product of the short circuit impedance and the open circuit impedance. So what is the short circuit impedance ZSC? That will be equal to shorting these two terminals. So these 2 points are the same. So we have ZA parallel with ZB, and here also we have ZA parallel with ZB. These two will be in parallel and these two will be in series. So short circuit impedance will be ZA parallel ZB plus ZA parallel ZB. So that will be twice of ZA ZB divided by ZA plus ZB. And what is the open circuit impedance? ZOC. So now this is open. So we have ZA series with ZB. And here also we have ZB series with ZA. And these two arms will be in parallel combination. So we have ZA plus ZB parallel with ZA plus ZB. So what is this? ZA plus ZB by 2. Question 2. Now we multiply ZSC and ZOC. So these two will get cancelled and ZA plus ZB and this ZA plus ZB will get cancelled. So in effect we have ZA and ZB. So what is Z0 for a lattice network? The square root of the product of short circuit impedance and the open circuit impedance. So square root of this will be equal to ZA to ZB. Now we will find out an expression for propagation constant gamma for a T network, for a general T network. So we draw the network like before. In which the total series arm impedance will be equal to Z1 and the total shunt arm impedance will be equal to Z2. So what is Z1? Z1 is the total shunt arm impedance will be equal to Z2. So this will be equal to Z2. This one will be equal to Z1 by 2 and Z1 by 2. So we have the sending end 1 1 dash and the receiving end 2 2 dash. And this symmetrical T network is terminated by its characteristic impedance Z naught T. Now Vs is the sending end voltage and Is is the sending end current. So we have the receiving end voltage VR across the load, which is the characteristic impedance in this particular case. So this network is properly matched. That is, we are attaching the characteristic impedance Z naught of this particular T network at the receiving end, and IR will be the receiving end current, that is the current that is going to flow through this load. Now we will take two loops. One is this loop, this one is the second loop. Now we will write the Kirchhoff's voltage rule for loop 1. So in loop 1 we have the sending end voltage Vs is equal to Is into Z1 by 2 plus, here it will be Is minus IR. Is minus IR into Z2. Now what is Vs? We are looking from this side. So when we look at this side, since this network is terminated by its characteristic impedance Z naught T, what will be the input impedance Zi? That will be equal to this characteristic impedance Z naught T itself. So we can write Vs, the voltage, as the product of the current, sending end current, into the sending end impedance. So Vs will be equal to, so on the left hand side we have Vs is equal to Is into Z naught T, and here we have on the right hand side Is into Z1 by 2 plus Is Z2 minus IR Z2. Now we collect the terms. Is Z naught T minus Z1 by 2 by bringing this to the left hand side minus Z2 is equal to minus IR Z2. Now why we write, what is our aim? Our aim is to find gamma. So we know that in lecture 2 we have defined the propagation constant as a relationship e raised to gamma is equal to Is upon IR. That is the ratio of sending end current to the receiving end current. So we need this ratio Is by IR. We will bring this Is below IR. We will absorb this minus sign within this bracket. So IR upon Is is equal to, and this Z2 will come here. So Z2 by Z2 will be equal to 1 minus will be cancelled, plus z1 by 2 z2 minus z0 t by z2. So what is this? So we have e power gamma is equal to is by ir. So what is ir by is? That will be equal to e power minus gamma. So on the left hand side we are having e power minus gamma. That is equal to 1 plus z1 by 2 z2 minus z0 t by z2. So we have one equation here. Similarly, we can write an equation for this second loop. So we have, so here we are traversing, we are in the opposite direction. Okay, so plus 2 minus. So we have minus VR is equal to, here we have IR minus IS. So IR minus IS into Z2 plus IR into Z1 by 2. Now what is the receiving end voltage? VR. That will be the product of the receiving end current IR and the characteristic impedance Z0 t. So we have on the left hand side VR will be replaced by IR into Z0 t is equal to IR Z2 minus IS Z2 plus IR Z1 by 2. I will collect the terms for IR. So we have IR minus Z0 t here, and this Z2 will come here with a negative sign, and this Z1 by 2 will also come to this side with a negative sign. Yes, Z1 by 2. So on the right hand side we have minus IS into Z2, this term alone. Okay. Now you can observe this minus sign inside the bracket, so all these quantities will become positive. Also we will take the ratio IS by IR by bringing this Z2 here, so that these terms will be cancelled. So what is IS by IR? So this is Z2 divided by this is Z2 will be equal to 1 plus this term divided by Z2 Z1 by twice Z2 plus this Z0 t divided by Z2. Now what is this left hand side? Is our e raised to gamma. So that is equal to 1 plus Z1 by 2 Z2 plus Z0 t by Z2. So this is our second equation. So we have these two equations. E power gamma is equal to 1 plus Z1 by 2 Z2 plus Z0 t by Z2, and e power minus gamma is equal to 1 plus Z1 by 2 Z2 minus Z0 t by Z2. Now what is sin h gamma? that is equal to e power gamma minus e power minus gamma divided by 2. So what is e power gamma? This minus e power minus gamma. So this quantity minus this quantity. So we have 1 plus z1 by 2z2 getting cancelled in the numerator. Okay, so we have z0 t by z2 minus minus of z0 t by z2. So that will be z0 t by 2 plus z0 t by 2. So that will be twice of z0 t by z2, and the denominator we are having 2 here. So these two will be cancelled. So we have sin h gamma is equal to z0 t by z2. So this is for a T network. So sin h gamma t will be equal to z0 t, the characteristic impedance, divided by z2, the shunt arm impedance. What about cos h gamma? That is equal to e power gamma plus e power minus gamma divided by 2. So this quantity e power gamma plus this quantity. So the cancelling term is z0 t by z2. So these two will get cancelled, and in the numerator we have twice of 1 plus z1 by twice z2. So we have twice of 1 plus z1 by twice z2. So this is our e power gamma plus e power minus gamma. In the denominator we are having this 2. So these will get cancelled. So for our T network, cos h gamma t will be equal to 1 plus z1 by twice of z2. So these two results here I have. So for a T network, we have sin h gamma t is equal to z0 t by z2, and cos h gamma t will be equal to 1 plus z1 by twice of z2. We need to remember this relationship, which will be used to further explain the filter networks. Now we will evaluate the propagation constant gamma for a general pi network. So just like before, we will draw this general pi network in a manner such that the total series arm impedance will be equal to Z1, and the total shunt arm impedance will be equal to Z2. So this should be equal to Z1, this will be equal to twice Z2, should be equal to twice Z2. And this network is terminated by its characteristic impedance Z0 for a pi network, Z0 pi. At the sending end, we have the sending end voltage Vs, and Is is the sending end current. At the receiving end, we have the receiving end voltage Vr and the receiving end current AR, which is going to flow through this characteristic impedance Z0 pi. So this network is terminated by its characteristic impedance Z0 pi, so that when we look at this network from the input side, the input impedance Zi will be equal to its characteristic impedance Z0 pi. This is as per the definition of characteristic impedance. And we have two nodes. This one is first node, this one is the second node. So what is the voltage at this particular node? 1. It will be same as this voltage, the sending end voltage Vs. And here we have the series arm impedance Z1, And on the other side of this impedance, we have the node 2, where we are having the same voltage across the load impedance Z0 pi. So this voltage at this particular node will be equal to VR itself. Now, for this particular pi network, we will be writing the Kirchhoff's current rules for node 1 and node 2. So for this particular node, we have an incoming current IS, and we have two currents leaving this particular node. One is going to flow through 2Z2 and one is going to flow through Z1. So we have at node 1 the incoming current IS, that will be equal to one current that is flowing through 2Z2. So that will be Vs upon 2Z2 plus current flowing through Z1. So what will be this impedance? Sorry, what will be this current? The difference of this voltage and this voltage divided by this impedance. So Vs minus Vr divided by Z1. So what is this IS? So it is the sending in current. So we have Vs as the sending in voltage and Z0 pi as the impedance of this particular network. So we are applying a voltage Vs across this impedance Z0 pi. So this current will be equal to Vs by Z0 pi. So on the left hand side we can write Vs by Z0 pi is equal to Vs by pi Z2 plus Vs by Z1 minus Vr by Z1. Now like before, we'll collect the terms for Vs and Vr. So here we have Vs is equal into 1 upon Z0 pi. So we have these terms minus 1 by 2Z2 minus 1 by Z1. And on the right hand side we have this term alone, that is Vr by Z1. Now we'll bring this Z1 to this numerator. We'll cross multiply like this. So we have the ratio Vr by Vs is equal to, here one minus sign is also there. So we'll absorb this minus sign within this equation. So this is Z1 divided by this is Z1. So that will be 1 plus minus will be absorbed here, Z1 by 2Z2 minus Z1 by Z0 pi. So what is on the left hand side? We are having the ratio of the receiving end voltage to the sending end voltage. So this is nothing but for e power minus gamma. So that is equal to 1 plus Z1 by 2Z2 minus Z1 by Z0 pi. This is our first equation. Now let us look at the node 2. So we have one current leaving this network, this current, and another current leaving this through 2Z2, and one current entering this network through Z1. So we can write the Kirchhoff's current law for node 2 as Vs minus Vr upon Z1 That is the current that is entering this node. And here we have one of the leaving current, that is VR by 2Z2. The second current is leaving through our load impedance Z0 pi. So that will be IR. Okay, so what is IR? IR is VR by Z0 pi. Again we will collect the terms for VR. So on the left hand side we have Vs by Z1 is equal to VR to 1 by 2 Z2 this term plus 1 by Z0 pi this term plus this coming to this side, it is 1 by Z1. Now how do we cross multiply? We will bring this Z1 to this one side, so that we have Vs by VR on the left hand side. So Vs by VR is equal to, so this Z1 multiplied with 1 by Z1, that will be equal to 1. Z1 multiplied with this 2Z2 will be Z1 by 2Z2. This is Z1 multiplied by 1 by Z0 pi is Z1 by Z0 pi. So what is on our left hand side? This is our e power gamma, that is equal to 1 plus Z1 by twice Z2 plus Z1 by Z0 pi. This is our second equation. Okay. So we have two equations. One is for e power gamma and one is for e power minus gamma. So what is our sin h gamma? That is equal to e power gamma minus e power minus gamma divided by 2. So we have e power gamma is this quantity. So this minus this. So 1 plus Z1 by 2 Z2 will be cancelled out. And this will be remaining Z1 by 2. Sorry, Z1 by Z0 pi minus of minus Z1 by Z0 pi. So that will be equal to twice of Z1 by Z0 pi. That is e power gamma minus e power minus gamma divided by 2. So our sin h gamma for a pi network will be Z1 by Z0 pi. Okay, now what is cos h gamma? That is e power gamma plus e power minus gamma divided by 2. Now what is the cancelling term here? Z1 by Z0 pi and minus of Z and minus of Z1 by Z0 pi. So we have twice of 1 plus Z1 by 2 Z2 here in the numerator. Twice of 1 plus Z1 by 2 Z2 divided by this 2 here. So this will be cancelled. So what we have is cos h gamma for a pi network is equal to 1 plus Z1 by 2 Z2. So this is the result, where gamma is called the propagation constant and gamma pi is called the propagation constant for this particular pi network that we have taken. We should also recollect that for T network, sin h gamma T is equal to Z0 T by Z2. Whereas for a pi network, sin h gamma pi is equal to Z1 by Z not pi. Whereas cosine gamma for a T network is cosine gamma T is equal to 1 plus Z1 by 2Z2. And cosine gamma pi for a pi network is equal to 1 plus Z1 by 2Z2. So these two have the same expression, whereas these are not having the same expression. So for a T and pi network, sin h gamma is going to vary, going to have different expressions. And for cosine gamma for T and pi network, we will get a similar expression, that is cosine gamma is equal to 1 plus Z1 by 2Z2. So like I said before, remember this expression, we will need this in the future. Okay, next we will evaluate an expression for propagation constant for a lattice network. So we will draw the lattice network like we did before. So we have series of impedances and the diagonal impedances So our series of impedances are ZA and diagonal impedances are ZB. And we have the sending end voltage Vs and the sending end current Is. And on the receiving end we have the load impedance, which is the characteristic impedance for this lattice network. That will be Z0, and we get the receiving end voltage VR across the characteristic impedance Z0. And IR is the receiving end current. Next we can write some currents here for this particular node, and here, and some current here. This current will come here. We have one current here. Let this current be I1. So I is the incoming current and I1 is leaving here. So this should be equal to Is minus I1. This current will come here. Similarly here I1 current is the incoming current and IR is the outgoing current. So this current will be equal to I1 minus IR. And for this particular node we have Is minus I1 coming here, incoming current, and another incoming current IR. So the outgoing current will be the sum total of this branch current and this branch current. That will be equal to Is minus I1 plus IR. Now we can consider two loops. One, let it be like this. Okay. One loop will be like this. So this loop is through here, going through ZA and coming back through ZB, coming like this. So that is loop 1. Similarly, we can also consider one more loop which is going through characteristic impedance Z0, and then going through this diagonal arm like this, and then coming like this, going through ZA. So this is our loop 2. Going through ZB and then going through ZA. So we can consider any loop. Okay, so this is one particular method that we are discussing. Now let us see what is the Kirchhoff's voltage rule we can write for loop 1. So we have Vs, sending end voltage, is equal to I1 into ZA and here we have I1 minus IR into ZB. Again, since we are attaching the characteristic impedance is not for this particular lattice network at the load, input impedance Zi will be equal to Z0. So what is the sending end voltage Vs? That will be equal to the sending in current Is into the total impedance of this particular network. So the total impedance is, when viewed from the input side, is our characteristic impedance Z0. So what is Vs? So Vs on the left hand side will be equal to Is into Z0. That is equal to I1 Za plus I1 Zb minus IR Zb. So this we can rewrite by collecting the term for I1 as Za, I1 into Za plus Zb, collecting these two terms, minus IR into Zb. So this will label as first equation. And then we will write the Kirchhoff's voltage law for the loop 2, second loop. So here we are traversing against the receiving end voltage. So we have minus VR, which is equal to, here also we are traversing against the current direction. So we have minus of Is minus I1 into Zb. Here we have I1 into Za. So what is receiving end voltage VR? That is the receiving end current, product of the receiving end current IR into Z0. So we have IR Z0 is equal to minus Is Zb plus I1 Zb plus I1 Za. So we can rewrite this as IR Z0 is equal to I1 Za plus Zb minus Is Zb. Now what if we subtract second equation from the first equation? So we have A minus B. So on the left hand side we have Z0 as common factor, Is plus IR on the left hand side, these two terms. And this one will get cancelled. I1 into ZA plus ZB minus I1 into ZA plus ZB will yield, that term will get cancelled. So we have minus of this will be plus. ZB will take common from this ZB into IS minus IR. So this is the right hand side. So we'll collect the terms of IS and IR separately. So on the left hand side we have IS into Z0 minus ZB. So that is this term. And on the right hand side we have the IR. So we have minus ZB here and minus Z0. Now we will bring IR to the denominator so that we have the ratio IS by IR. And we will absorb this minus sign within here. So we have IS by IR is equal to, we bring this to the denominator. So the numerator we have ZB plus Z0, and the denominator we have minus, so we have ZB minus Z0. So what is this left hand side? This is our e power gamma. So that is equal to ZB plus Z0 divided by ZB minus Z0. Now we have a relationship that we have also discussed this before, that is tan h of 2x is equal to tan h of x is equal to e power 2x minus 1 divided by e power 2x plus 1. So using this we can write tan h of gamma by 2 is equal to e power gamma minus 1 divided by e power gamma plus 1. So what is this? This will be ZB plus Z0 divided by ZB minus Z0 minus 1 divided by e power gamma is again ZB plus Z0 divided by ZB minus Z0 plus 1. So what it will be? Plus Z0 minus ZB minus Z0 ZB plus Z0 plus ZB minus Z0. So we have ZB cancelling here, and it will be twice Z0, and here we have Z0 getting cancelled, we have twice ZB. So 2 will get cancelled from numerator and denominator, we have Z0 by ZB on the right hand side. So this is our tan h gamma by 2. And for lattice network we have already seen that Z0 is equal to square root of ZA and ZB. So bringing this equation, tan h gamma by 2 is equal to z0. Z0 is za into zb divided by zb. So that is equal to this zb and this will get cancelled, a by zb. So the propagation constant for our lattice network tan h gamma by 2 is equal to root of za by zb. So with that we conclude our lecture 3. So in this lecture we have seen the expression for the characteristic impedance for a general T and pi network. Also we have seen the expression for propagation constant for T and pi network. Also we have established a relationship for the characteristic impedance for a general T and pi network, where the total series sum impedance is equal to Z1 and the total shunt-arm impedance is equal to Z2. Also we have derived expressions for the characteristic impedance and propagation constant for a lattice network. In the next lecture we will see how we can realize a T network and as well as a pi network in terms of its short circuit and open circuit impedances. Also we will see how we can represent a T as well as a pi network in terms of its characteristic impedance Z0 and propagation constant gamma. And we will be doing some tutorial problems, as well as we will be seeing the case of a lattice network. Thank you.